I thought this was interesting. We can see how someone grows according to the square cube law. So for example, how does a kid grow into an adult? Also, we can get the average cross-sectional area of a person. So just a bit of trivia. Normally, you'd think if you're going to get the cross-sectional area of someone, you'd have to measure the feet and wrist and calves and waist and chest and neck and head. But turns out it's really easy, and I'll show that just using a person's density. Next up, I'm also going to show how you can actually use a wrong proxy number. I just call it a proxy number because it's just some random number. So we can actually use a wrong number to get the right answer in a formula. Just plug in any random number and you'll still get the right answer. So I thought that was interesting. So let's take an average size 12-year-old. Let's say it's a male, so he can grow to be 6 foot tall. Women can grow that tall too, but more common for men. So let's say he's average 12-year-old, 5 foot tall, 100 pounds. This puts him in the ballpark of the 60th percentile on the pediatric growth charts. You can actually print off those charts and use a straight edge to get a more precise number, but I just saw that these numbers were somewhere between the 50th to 75th percentile. So this means that about 60% of the population is below this kid in both height and weight, and about 40% is above him on average. So if we're going to grow him from 5 feet tall to 6 feet tall, first thing we need to find out is how much of an increase is that. We can just take 5 foot times a certain amount equals 6 foot, solve for x, and we will get 1/5 or 20%. So he will get about 20% taller. And I almost forgot to show that right here. And notice here we will have foot divided by foot, 1 foot divided by 5 foot. The feet cancel, so we have no units, just 0.2 as a unitless number. And next page. Just to show how this wouldn't work, if this was a linear growth, meaning that his weight was directly proportional to his height. So if he's 20% taller, that would mean he's 20% heavier. So let's take his 100 pounds plus 20% of 100. That means he would only weigh 120 pounds, which would be a relatively emaciated 6 foot tall person. And again, that's with a linear growth and not multiplicative or using the square cube law. So now I'm going to show how he can grow with the square cube law. First, we'll just use some basic geometric formulas. Height times area equals your volume. We got the height of a bunch of cubes. We have x for the area of the cube. So let's see here. Next up, we have mass over volume equals density. But since volume equals height times area, we just switch out volume for height times area. So mass divided by the quantity, height times area, equals your density. And that volume equals the height times x squared, or height times x, or height times area, if I didn't already say that. So mass divided by the quantity of height times x squared will equal the density. I'm going to give a person the density of water because that's approximately the density of people. If a person has low body fat, they will be more dense than water and sink. If they have more body fat, then they will be less dense than water and float. And a lot of people are what you'd call about neutrally buoyant. So if they take a deep breath, they float. If they let the air out of their lungs, they sink. So a person's overall density depends on how much air they have in their lungs. I'm going to use a person with the density of water here, but you could actually theoretically find the density of any person. You just weigh them and then put them in a tank of water and see how much the water level goes up to get their volume. And then you just have to decide if this density will be with air in the lungs, with full inspiration or full expiration, or somewhere in between. I was thinking I saw this a long time ago, and they tell people to try to let the air out of their lungs as the standard, but I'm not sure on that. And next page. And for the next calculations here, I'm going to use centimeters, or as the old timers say, sonometers. Whenever we have older professors lecture, I noticed throughout my life, they would use the term sonometers, but younger people use centimeters. So I'm thinking sonometers might be more of a French pronunciation, don't know. At any rate, we got our 12-year-old, 100 pounds, 5 feet tall, again, 60th percentile. Change everything into kilograms and centimeters, and we are just going to solve for x. So what we have here is the density, which is mass over volume. We have the height. We need to find out the area, which will be x squared in centimeters. That'll equal 1 kg per liter, or 1 kilogram per 1,000 cubic centimeters, because that is the density of water. Go through the algebra and solve for x. We get x equals 17.26 centimeters, or 6.8 inches in one dimension. You square it, you'll get 46 square centimeters for the average cross-sectional area of a person. So I think that's some interesting trivia. The average person is about 6.8 inches across. All right, so now what we're going to do is turn this information into the person's new weight. To go from 5 feet tall to 6 feet tall, or 152.4 centimeters to 183 centimeters, it's a 20% increase, or 1/5. So since we know that the height is increasing by 20%, then that means every dimension needs to increase by 20%. Let's take our 17.26 centimeters for each dimension on the area, increase that by 20%. And so we will get 20.7 centimeters. So it'll be 20.7 centimeters quantity squared for the area, and then times 6 foot for the height, or 183 centimeters. Our new volume will be 78,504 cubic centimeters, because we are multiplying square centimeter times centimeter to get a cubic centimeter. Multiply that times the density, and that will equal, let's see, 78,504 cubic centimeters times 1 kg per 1,000 cubic centimeters. Cubic centimeter divided by cubic centimeter cancels. That's why I always do conversion equations. We're left with kgs, so we end up with 78.5 kgs, or kilograms, which also equals 173 pounds. This is a little on the thin side for a typical 6 foot tall American or somebody in a developed country, I suppose. But there is actually no normal weight for somebody of a certain height. So for example, if you look at a marathon runner that's about 6 feet tall, they will weigh under 150 pounds. So if you were to take the BMI, or body mass index, of all the marathon runners that show up to run a race on a certain day, that bell curve will fall within a certain range. And then if you take the BMI of a bunch of people going to the gym to lift weights and have a lot of muscle mass, they're going to have a BMI bell curve fall in a different range. And same way if you just take the BMI of a bunch of sedentary people. So it's good to remember that in nature there are a few certainties. There tends to only be bell curves, and everybody will fall within a certain number of standard deviations from the mean on a bell curve. Also, it's a good idea to keep our minds open to any possible nuances that could come up and bite us if we don't think about them. For example, toddlers will have proportionally larger heads and proportionally smaller limbs compared to adults. But I'm thinking by the time they reach 12 years old, those proportions should be about the same as adult proportions, but I actually never looked into it. It's also good to consider that maybe theoretically adults could have denser bones, which would give them a heavier weight also, but that may not be true. I'm just keeping my mind open to any possibilities on how this number might not be perfectly accurate, or keeping my mind open to the possibility that I could have missed something. On the next page, I'm going to show how you can actually get this same answer with just using a proxy number that's wrong. This is how I originally did the problem, because I didn't think of getting the person's density and average cross-sectional area. Usually when I get an idea for a video, I just think, hey, that's kind of a fun fact, and I just scratch down a whole bunch of notes really fast and make a video, and I don't give it much thought. And then days or weeks could pass, and then I start thinking about more details that make it more interesting or more accurate. So at any rate, this is how I originally did it with the square cube growth. Take a 5 foot person. Let's just make up an average area for cross-sectional area. Let's just say it's 1 foot by 1 foot. So 1 square foot. And I came up with that number because if you hold a ruler up to a person's chest, it's approximately 1 foot across. But this 1 foot number right here totally does not matter. You can use any number you want to, so 1 square foot is a pretty easy number. And the only reason we need this number is because we need to give this person a volume so that when they grow from 5 feet tall to 6 feet tall, we can grow that area in the same proportion. So we can grow that whole volume in the same proportion. And if that area turns out to be wrong, we just end up with a different density of the person, but we'll still end up with the same growth of the actual mass. So that's why the numbers work out. So let's take 5 foot times 1 foot times 1 foot. And so mass over volume equals your density. 100 pounds over 5 cubic feet equals 20 pounds per cubic feet as our made up density. And I just left things with imperial units here because that was easy enough. So they grow from 5 feet tall to 6 feet tall. That means they increased by 20%. as I showed earlier. So let's take that 1 foot across, 1 foot by 1 foot. Let's grow that 1 foot by 20%. We get 1.2 feet. So now the dimensions of our new person, our 12-year-old that grew to a 6 foot tall 20-year-old. They are 6 feet tall, and their dimension is 1.2 feet for the area. So 1.2 feet times 1.2 feet times 6 foot gives 8.64 cubic feet for the volume. Multiply that times the density, 8.64 cubic feet times 20 pounds per cubic feet. Cubic feet divided by cubic feet cancels. We're left with 173 pounds, the same answer as before. And here I just said considering nuances, adults tend to have more muscle, or a higher percentage of muscle and higher percentage of fat compared to a skinny 12-year-old. And I noticed, just as a fun fact, pro fighters, a 6 foot tall pro fighter will weigh in at about 170 pounds, but that's after typically losing 10 or 15 pounds of water when they cut weight. So again, it's always good to remember that everything in nature tends to fall in a bell curve, and an individual's diet and activity level will determine where they fall in that bell curve. And it also depends on from what population you derive that bell curve, whether it's from marathon runners or bodybuilders or whatever. So that's it.